Okay, we're going to be doing LeetCode 617, merge two binary trees. So you are given two binary trees, root 1 and root 2. Imagine that when you put one of them to cover the other, some nodes of the two trees are overlapped while the others are not, right? As you can see here. So these two will overlap, but these will not because there's none here. The merge rule is that if two nodes overlap, then some node values up as the new value of the merged node. Otherwise, the not null node will be used as the node of the new tree. Return the merged tree. The merging process must start from the root nodes of both trees. So the way to solve this was confusing me, but the way to solve it is to simply use one of them as the, you can use either one of them as the tree that you're going to return. So you simply, if they both exist, you simply add their values into one of the nodes, right? If you're at a certain level, at a certain node and they both exist, you add them into that node. And then if the other is null, you return the one that is not null. And if both are none, you simply return none, right? So let's do it. It's very simple, right? And I'm going to explain to you how it terminates. So first condition, both nodes are none. We simply return none, right? So if root 1.val, let's use the Pythonic way. If not root.val and not root 2, sorry, not val. If not root 1 and not root 2, you simply return none, right? Second condition, one of the nodes is none, the other is not. This will be if not root 1 and root 2, you return the one that's not none, right? Which in this case is root 2. And then if root 1 and not root 2, you actually return root 1. The third condition, the third case, first case, not condition, first case, second case, third case is both nodes exist, so they overlap, right? So all we do, you can either do root, you can do it like this, root1.val plus equals to root2.val, or an alternative would be root1.val is equal to root1.val plus root2.val, right? So once you do that, we recursively call to populate the left and right of root 1. But remember, this could have been root 2 if we had chosen to merge into root 2, right? So we say root1.left is equal to self dot merge trees root 1.left root 2.left. Then root 1.right is equal to self dot merge trees root 1.right root 2.right. Okay. Then here we simply return root 1. So this terminates when we reach this case, the nulls, right? Which is when we go past the leaves, it will simply return none on each side, like here and here. That's how it terminates. So it should work. And voila, it gives us 69. Give me 90. Come on, perfect, 91. So yeah, this is the solution, and it takes all of n time with constant space, where n is the number of nodes, right? So using recursion, yep, here they did it in a cleverer way here, but number of nodes, the depth of the recursion tree can go. Oh yeah, since we're doing it recursively, then you're going to have the call stack be the number of nodes, right? And even if we did it iteratively, we'd have a stack complexity of about O of n. So yeah, that's the solution. It's not a constant time complexity. So thank you and bye.